All right, in this lecture, we're going to talk about latent heat. So, in a previous class, you did a time versus temperature experiment, right? Where you, as the time went on, you recorded the temperature. You should have seen things where it was leveling out. And the question is, why is that happening? Why do we see this leveling out, even in temperature, even though we're still having heat added to it? Part of the reason for this is because when we change states, this isn't a chemical reaction, especially if it's just one substance changing state and we're applying heat. But what's happening is, right, we have these things called intermolecular forces that hold molecules together. Right, so this is different from a bond. So an individual molecule, right, so let's say water, right, this has, right, these are the bonds between the elements. The intermolecular force is keeping another water molecule nearby and close together. But when we change states, that's going to either pull molecules apart or bring them back together. So right, if we're going from like solid, liquid to gas, right, we're pulling them apart. So we're going to have to break those forces. And that's why even though we're applying heat energy to the system, we're not actually, it's not actually rising in temperature because that energy is going into breaking apart those molecules from each other. So not breaking the bonds, but pulling the molecules away from each other. Right? So latent heat, this is the energy involved in transitioning a substance between states. So, right, so what we were just talking about, we call this latent heat. An example of this, right, boiling water. We need to add a lot of energy to convert water to steam, but there's not going to be any temperature change during that time. Now, right, if we're applying energy to take water from liquid to gas, when we go from gas to liquid, it's going to release that energy back out, right? So in a storm, right, it's going to actually release heat. So you probably know, well, hopefully you notice that when like clouds come overhead, it actually warms up a few degrees because of that water being condensed above us, right? Because clouds are just condensed water. This will then heat any body of water nearby, for us the ocean. That's going to increase evaporation, and then the storm is going to intensify. So right, storms are like feedback loops with each other. The condensing water causes more evaporation, causes more condensing water to have the storm and as it moves along. Some real world impacts. So water has a large latent heat, so that means it takes a lot of energy to change states. So this means ice can last a long time if insulated. If you ever go camping and you have a cooler, right, the ice in it should last a long time, and you might find yourself emptying the water out that does collect, so that way the ice will last longer. The ice caps in oceans are pretty stable in their states, which is really a good thing for us since they control a lot of our climate. And then hurricanes get so big because of this feedback loop that we talked about on the previous slide. There are two types of latent heat. Heat is also called enthalpy. So in your book, you're going to see it called enthalpy, but it's the same thing. It's just heat's a simpler word than enthalpy, so that's why we use that more. So first we have enthalpy of vaporization, which we symbolize by H subscript V. And this is the heat needed for the vaporization of a liquid at its boiling point temperature. So boiling point is the point at which it boils. And we see it around here, right? So where water and steam are where it leveled out in temperature, right? That means that all the energy being put in is going to changing the water or the liquid into steam. Heat of vaporization is also for the reverse. So it's always, if you find the question is involving gas and liquids, it's talking about vaporization. The other one is enthalpy or heat of fusion. We symbolize by HF. And this is the heat needed for the melting of a solid at its melting point temperature. So melting point, that's when it melts, the temperature at which it melts at. And we see that here on the graph where it's ice and water and it's stable at 0 degrees because the energy, right, is going into changing the solid into liquid. Again, fusion is always just going to be referring to solid and liquid. All right, so let's do a problem involving latent heat. So the question asks, how much energy would be needed to convert 630 grams of ice into liquid water? And we're given the HF. And this is actually an incorrect HF, but we're going to do the problem based off of that. So now I haven't given you the equation for latent heat yet, but let's figure it out. So if we see that HF is in grams or joules per gram, all right, so I'm going to write that down here, joules per gram. Let's think about this. Joules are the unit of energy, and we symbolize energy with Q. Grams are the unit of mass, and we symbolize mass with M. So the equation for this is heat of fusion is equal to Q over M. And then we can get rid of this down here. No, I can't. Okay, so now let's do the problem. So the question, right, we're looking for the energy required, we're given the mass, and we're given HF. So Q is what we're looking for. So we want to isolate Q in our equation. So if we have HF is equal to Q over M, if we multiply both sides by mass, then we get that Q is equal to mass times HF. All right, so then we just plug in the values we're given. So 630 grams, 224 joules per gram. You can see grams are on opposite sides of the dividing line, so they're able to cancel with each other. And we find that Q is equal to 141,000, around that. All right, so those are how you solve problems with it. There is a worksheet on latent heat for you to work on now.